Welcome back, everyone. I hope you had a nice lunch and is ready for our second session for today, which is the session on digitalization, digital efficiency and future technology of the maritime sector. It should have been chaired by Mr. Reinhard Lüken, but unfortunately he had some very important business to attend to, so I'm left with the challenge of trying to steer the panel we have in front of us with 4 panelists speaking on these very issues. I think we should get on with it, and I'll introduce people as we get to it. And our first speaker is Mia L., who is a R&D manager from Delta Marine. She will speak about shipping, decarbonization, and digital threat. Mia, please.
All right. So let's see if this works. So welcome from the lunch. Hopefully you're awake. And basically, let's see if it's not on. Okay, a couple of words about Delta Marine, just to get you a little bit on board. What is my presentation about? So Delta Marine, we are a ship design company and focusing actually on all kinds of vessels. So both cargo, passenger segment, also offshore. And our services cover actually the whole life cycle of the vessel, of course, focusing on the design aspects of it. And personally, as an R&D manager, I've been already working for 15 years at Delta Marine, so my focus has been typically the energy saving related issues and various integrating new technologies, basically, on board vessels. And this digital design topic is, of course, very familiar to me as well. So coming from that background, so I think it's actually good to start with kind of setting the purpose for the digital design, because all kind of, I think, digital models and digital twins, they are not the purpose, but they are the tool. So typically now, if we want to decarbonize or reduce environmental impacts of the vessel. So here's now at least one example of many different kinds of items, what we can utilize in order to reach certain level of performance. So, of course, important part is to consider the ship operation. We can actually just by operational optimization reach certain point or certain kind of efficiency. Then the second group, I would say, of decarbonization is related to the technical optimization of the ship and the systems, the machinery and the hull and all things, and also some, let's say, post-processing such as carbon capture also could be calculated to this group. And then, of course, when all of that energy efficiency is maximized in various ways, so then still probably we need some energy to move the ship, so then the alternative fuels and the low carbon fuels come into the picture. Because also it's of course a little bit kind of a unique which combination is suitable for each case, but we could also think about it that this order of kind of presentation is that if we want to look at also the cost side of things, so typically let's say the blue box there in the left side, so that is giving us a lower, let's say, cost per reduced carbon ton compared to then these alternative fuels. At least when we really go into this kind of a full zero carbon or really carbon neutral operation. So of course this can be debated, but also based on quite much research in the area. So anyway, typically I would say that it makes sense at least to start from the energy system optimization and then go forward with these fuels. And anyway, all of this has to be considered at the same time. So we cannot really do one thing and without thinking that it has an impact to all the other aspects as well. So if we now have these decarbonization options in mind, what we want to introduce in the ships. So basically from the kind of global optimization point of view, so there is, in addition to these technical items what we can do as a designer, for example, introduce to ships. So we have to think of the time dimension, and not only the ship operational time dimension, but also the ship life cycle dimension. So of course, from the cost perspective as well, so it is kind of a straightforward to consider these things at the start of the project during the conceptual design of the vessel. So if possible, to really design a new vessel, so of course all of these technologies and these kind of decarbonization aspects, which might be coming actually in the picture only later. We've seen a lot of designs, and we also have been designing vessels that will be operating with another fuel in the future, for example ammonia, but the vessel will start with another fuel, diesel or LNG. So it is still important to be able, in the beginning of the project, to be, for example, simulating or optimizing to some extent the ship with these kind of future technologies, or maybe there will be another kind of operational profile for the vessel. So I would say that there has to be good understanding of the anatomy of the energy and anatomy of the decarbonization for the vessel. So basically for that purpose, it's very efficient that we have digital models which are helping us, or they are then the tool that we can use to analyze which technology, which strategies is good for this ship, for this specific route. So I like to kind of see these means or these digital models to be built basically around three kind of topics. So the first group, I would say, it really kind of includes maybe the traditional ship design, where we have the ship hull, volume, and the structural model, and of course the layout and that type of things. But then the second step in the digital modeling, in order to be able to kind of catch the aspects of the operation, so we should have also then combined to this kind of a digital ship in a vacuum. So then we have to combine a digital model of the external forces. So for example, weather, waves, depending on the case, I mean shallow water, that type of things of course are relevant. Then the final box is kind of my baby, so it's the energy model, which then is kind of the step where we then combine the propulsion profile to the, let's say, functional model of the ship system. So all those engines and shaft generators and batteries we are then placing potentially within the ship. So how do they actually work? So the energy side of things, what is the energy consumption of the ships, electricity and heat-wise, and then also the machinery, the fuel. So all of that is then combined in the energy model, and that is then feeding the, let's say, results of what is our, for example, fuel consumption, what is our carbon intensity, what is CII, and so on. So basically, in our world, of course, at Deltamarine, we like to deltamarinize everything, so we have even names for all of these boxes. And in this case, so as said, so the delta weight, the first box we use for getting, of course, the basic model of the ship in general, and this is where the hull optimization typically is started. But then the data layer, so that includes the weather, and eventually then the energy model, then kind of this is where we calculate basically the KPIs, key performance indicators, for the vessel. So basically, I would say that kind of making these digital models work for the decarbonization. So it's really essential that we start by setting targets for the project and setting targets for this kind of carbon performance. And then the second thing is really to set relevant kind of focus areas. So focusing, of course, if we are starting the conceptual design, so then of course we start from the main dimensions and that kind of things. But if we are doing a retrofit, so then of course we focus on a little bit more details. And now I was thinking that I will show a couple of now practical examples, because this is a little bit theoretical. So from some recent projects where actually we are putting this whole, let's say, digital modeling into action. So because then it's also kind of important thing is to also that when making the digital models, so it's possible to kind of make continuity. So if digital model is created in the conceptual design, it's of course possible to use it later on for building more details, and then also to verify the performance later on, verify the design performance. And here's one example of the current projects we are working with, where actually we are doing all this digital story in a very compact way. So we are talking about the 3-year EU project called CHECK. And in this project, so we are focusing on decarbonizing long-distance shipping, where we have actually 2 very different kinds of ships. So we have a bulk carrier and we have a cruise ship. And here the idea is to kind of study the decarbonization first. Let's say the ultimate solution is that we have a lot of project partners here. So Wärtsilä is making a hydrogen engine for the cruise ship. And then we are looking at, for the bulker, then either bio or synthetic LNG machinery as the ultimate kind of decarbonization solution. But before that, so we have a 40 to 50% energy saving target compared to a baseline, which is set for typical EEDI2 compliant vessels. So as said, so then this energy saving part, so we are looking at certain aspects of hull design, but also mostly kind of combining very different technologies and also operational strategies such as weather routing. So from the technologies, so for example, for the bulker, we are looking at these bar technology sails and Yara Marine implementing them, and then gauge rudder. We have also silver stream, air lubrication. We have climate and waste heat recovery and hazy deck ultrasound, hull fouling prevention, and there are many more technologies. And so basically, I could just since time is somewhat limited, so I can just give one example where you see certain aspects when you start kind of modifying or modeling ship digitally. First of all, Delta Marine's role in the project CHECK is to perform this modeling in 3 different generations. First generation is digital prototype, or was digital prototype, where the point was actually to utilize, gather measurement data from operating case ships that give us a certain baseline of what is already kind of achieved typically in ships. And then we performed actually the energy modeling utilizing quite further measured data. And then we combine different technologies on top of that to give us an understanding where we can get with that technology mix. And now we're at the second phase, which is called Digital Master, where we have then actually created ourselves, we have created a hull for both of these ships, so that we are now able to get a little bit more kind of more details and understanding of the performance regarding these propulsion related technologies. And we are also making quite much cooperation with the partners here. So what we are looking at here, it's a kind of, let's say, working process, we can say, from the cruise ship. So what we see here is that, and this highlights you a little bit the process that we just chose here to show one example of let's say there's measured, actually, 1 7-day measured cruise, one, let's say, random week of cruise in Mediterranean in our, let's say, reference ship. And then the green part represents one, let's say, chosen week of operating where we have created a model of the hull. And then we have also, based on the operation, typical waypoints for the ship. We have chosen the waypoints and then, of course, related speed, and also gathered then data of the weather. So, and this is now data for 1 week in the past. And here what we can see is that if you look at one single cruise, and we are comparing the green one, the simulated one with the measured one. So for example, and this model is still missing the hull fouling. So we can see basically that there is one area which is not correct. So of course, in this case, if we would only look at one cruise, then we would, and actually we looked what happened. So it turned out that, okay, this wasn't a case of shallow water, it was just actually this day for the measured one. So there was just a much rougher weather. Because then, of course, how this kind of model is utilized is that we run in many times in the, let's say, many different cruises. So then we get an average performance. And then when we, of course, saw that the average performance is on the same level than the reference, so then we can conclude that this is a rather usable model which is representing rather accurately the typical operation. And with this kind of model, for example, we can study then, for example, alternatives for the itinerary of the vessel. So it can be useful in that case. Then I have some very short examples here in the end also of some other kind of digital modeling and what we can kind of conclude of that. I was actually here 2018 giving a presentation of when we were designing Viking Glory. So this is a ship designed by Delta Marine, and she was built in China and just started operation actually spring this year. So we don't yet have so much data that we could kind of finally verify the operation. There's not enough total kind of data, but of course here again this is a good example of this kind of verifying digital models. So typically I think it's a good idea to do it piecewise, because here in this project we had a huge focus area on hull and propulsion efficiency, and then secondary also, of course, machinery efficiency, and then there's a quite complex waste heat recovery system in this ship. So in this case, at this stage, of course, what is possible, we looked at our targets, reference propulsion profile, then we can look at the speed histograms, and when we are looking at what was the outcome, so we are now at least happy to see that the propulsion is working even a little bit better than it's supposed to be, because this is a larger vessel than our reference vessel. We have total 1 lane extra. But then what happens with the other systems when you kind of dig down into details? So for example, as I said, we have here steam turbines and 2 different kind of organic cranking cycles, transforming heat into electricity. How to then actually verify this kind of performance? So here we also here's a couple of examples. So then it's possible to collect, of course, data of the ship automation system and then go collect with certain heat flow measurements in this case to verify that how much heat we are actually putting into these systems. And again, with this kind of process, it's possible to verify that the models actually, models versus reality. And in this case, we could just say that it is actually, it is performing as basically it's supposed to, because in these kind of processes, typically it's not only the unit, but we are actually, this kind of a waste heat recovery unit is working behind basically waste heat recovery loop, which is working behind the engine, actually, heat recovery. So there are many steps where basically you can lose some energy. So this is a practical thing. And then I can just, since I was turbocharging a lot of things into this 15 minutes, so just kind of a final conclusions to me is that these digital models overall, so they really help in this kind of putting really numbers and understanding the decarbonization. And it's really the biggest impact can be made in the as early as possible stage. And also then if we do retrofits, so this has to be done rather fast. And it's always possible to build more details, but it's important to do verification whenever possible. And typically verification has to be done piecewise because there's never that same day you cannot exactly verify the vessel with or without certain technology because there's never exactly same kind of weather. So I would say that all of these digital models, throughout the ship lifetime, so they help also to define and focus the digital twin, which probably is coming next. Thank you.
Thank you, Mia, for a very interesting presentation on how you can optimize from a theoretical standpoint of ships. And I think it just reconfirms what has been said all along today, that we should never forget ship efficiency as one of the primary things we can deal with today. Our next presentation, the digital wave, It's performed by Gregory Puckett, Head of Group Digital at MAN Energy Solutions. Gregory, please take the floor.
Thanks. What an exciting time. I mean, technology coming together, right, to change the world from decarbonization, followed by digitization or accompanied with that. I mean, each one of you have taken the obligation to really change big things to zero, right? I mean, we're not talking about small things we're changing the entire maritime industry. I think that's a hell of a charge for all of us. And I'm excited about it. It's exciting because we're changing the world, we're attracting new talents, right? We're working with really cool technology. I mean, who would have thought 3 years ago we would be moving at the pace we are today with decarbonization? Would any of you have thought that? Okay, before we get started, I have a quick poll. How many of you have a cell phone? Raise your hand. Okay. How many of you have 2 cell phones on you? Raise your hand. Okay, we have some digital natives. Good. So you guys are already digitized, right? Even in the maritime industry, you've taken the step to digitize, and it's part of your daily life. So what I'd like to talk about a little bit is decarbonization, digitization. So when I started in digitization, MAN, I started out as digitization, almost its own standalone business sort of thing. We were going to build the platform that ruled the world like most of the industry. People were going to come running to use it. Wow, things were really going to change based on digitization alone. But we know that's not the case. We know that digitization can only accompany when there's a valid business reason behind it, and that's decarbonization. Because decarbonization requires data, and a lot of data, how do we come to that conclusion? It's through digitization, right? And in order to achieve the targets that we've all said we want to achieve here, we need to really drive for digitization. And digitization, as you just saw the colleague present, we need the data, we need to make intelligent decisions, we need to make real-time decisions, but we also need to make good conclusions that are reportable to class society. We need to have proof that we're meeting CII, that we're meeting all of the new regulations. The wave, by definition, what is a wave? Well, it's this continuous movement. And those of you who are the digital natives in your companies and in this industry, I've been doing it in this industry for about 5 years. I mean, they didn't call it digitization before. It was remote connection. You've sensed or saw the resistance in digitization in the industry. I hope all of you acknowledge that. Either A, we didn't understand it. B, cybersecurity wasn't there. C, there was no value proposition, right? Someone wasn't paying for it. There wasn't a cost. So this wave, by definition, is continuous. And each time we derive a new digital feature or function, these waves and journeys come up. And each of those words sort of depict the journey that we're taking. Cloud to cloud, what is that? You know, do any of you know? Platform, edge, all of these buzzwords that we're all working with that are now coming day to day, you know, vocabularies in our life. I mean, digitization is among us, just like some of you have 2 mobile phones or 1, you're already digitized. Now you just need to onboard some of these new terminologies into the business value. The wave's also been a continuous movement. I mean, for us at MAN, we started with connectivity, and that has been a hell of a difficult journey. I mean, some of you know it, whether you're an owner or you're a class society or whatever. Connectivity on a 2-stroke seagoing vessel is hard, right? And I've connected a lot of things in my life, from cars to medical devices to tractors. And I have to say, a 2-stroke vessel out at sea is so difficult to connect, and you can't do it alone. And then we have these platform applications. What's that? right? And we hear analytics and machine learning, and then digital partnerships. And yes, those are actual partners of us in MAN, and I'll describe a little bit of those. But this continuous movement, how do we connect retrofit vessels? How do we crack the nut of connecting new buildings? I mean, we're constantly exploring how to do that. How do we grow our platform to onboard the vessel to in the cloud? How do we come up with the analytics that you, as a partner or customer, can understand? How do we visualize it to make it relevant? And then finally, which digital partnerships do we select? There's a lot. Everybody wants to partner, right? Everybody wants an MOU. Hey, we have a press release. That's so cool. But the question is there fruit out of those partnerships? That's what matters. So I'll talk a little bit about connectivity, and it's the context of waves, because in former times I used to like to surf, and some of you are seafarers. So in the beginning, there was no silver bullet for connectivity. Somebody had to go on site, they had to install some hardware, they had to describe a value proposition, or it wasn't even clear. Customers said, hey, why are you adding more connectivity to my vessel? I already have every OEM in the world with a black box there. And then as the waters calmed, key thing for us as an OEM, and I'm sure for some of you, sales folks, right? We had to teach them about cybersecurity. We had to teach them to move from selling metal to digital. Think about that. We have great salespeople in MAN, and they have great solution mindsets when it comes to EXI, or you want a new turbocharger, or you need a new cylinder wall. Now, I'm trying to explain to those salespeople the value of digitization. It's been a journey, and I would be lying if I said it hasn't. It's getting better because the value proposition is becoming clear. Folks are understanding some of these terms we throw around like cloud and so on. And then I think the digital partnerships, particularly in the two-stroke industry. Let's face it, MAN is very fortunate to have a large presence in the two-stroke industry. But in order to connect to those two-stroke vessels, we need help from our licensees. We need help from our customers. We need help from our partners. How to get the data, right? How do we all get the data in order to have a more efficient vessel? And then I think connectivity also moves us to a safe on, let's say it's safe to swim. We're coming out with a product called Advice on Vessel, right? We're actually giving advice on board the vessel, not only in the cloud, to vessel and from vessel, so that we have a holistic picture of what's going on board the vessel for you. We have mobile applications now. We have data services where a lot of customers would just like to, instead of subscribing to an advisory service, they just want to get the API. So we've grown our portfolio based on what our customers need. So connectivity, and I know there's a couple of you I know personally in the room who are doing nothing but connectivity of your products. Platforms and applications. So again, in the beginning, we had a one ring to rule them all from Lord of the Rings, meaning that MAN, we have 3 different business segments. We have an industries business segment. We have 4-stroke, well, we have marine and power 4-stroke and 2-stroke. And believe it or not, all those businesses are different and they have different requirements, right? So the lessons learned from me is really understand the segment that you're serving. A 2-stroke vessel will have a different need than a 4-stroke vessel. A turbo machinery, or let's say heat pump or other technology, has different needs. So as the waters calmed, we learned that. Now we have an advanced engineering platform where our engineers can also have a look at the data to make our products better, to ensure that our engine designs just get better and better. I think the other thing with platforms and applications, if you just bring in a bunch of Microsoft guys and software developers and you forget about the domain, you have a real problem there. So the cool thing about MAN is we do have the best domain experts with our engines in the world. We have amazing guys. And setting them next to software people and data scientists and analytical folks, the ability to come with solutions at a speed is amazing for us. I think the other safe to swim for me is we have aligned applications on the vessel based on the use cases, from CII to performance and fleet advice, right? So we have an application now where you can understand what is the performance of your vessel, what's the performance of your fleet. And this has been significant, and I've talked to a few of you who are customers in here who have seen it, and the feedback is amazing. And the question is, how do we continue to grow that, to allow third-party applications on board the vessel? How do we digitize our documentation, which a lot of you love, to bring it closer to you as a customer? So again, these are the waves of digitization. Now, the reason I talk about these things, similar to decarbonization, these are all transitions, right? There was no digital transformation in the marine industry, sorry to say. It's a transition. And I would say, what lessons can we learn from the digital part into the decarbonization part? Because there's a lot of correlations. I think my most favorite term I hear a lot in the maritime industry is machine learning and AI. But let's face it, most of the analytics we use in the maritime industry, they're rules-based. They're physics models. They're if-then-else statements. But as we get more and more data from vessels, then we can derive machine learning. And so we've been focusing on variants of different engines. If it's the ME engine within the two-stroke, for example, we have machine learning models that we're able to roll out and provide to customers. We will continue to explore those variants. We do a lot of pilots with customers to get the feedback on the models. And I hope if some of you in the room get pinged for that, that you support us. Partnerships, this is my favorite. Again, let's sign the MOU and get an agreement. Let's sign one with DNV. Yes, we have a MOU with DNV. That's amazing. But the cool thing is, the CEO of DNV and my boss, the CEO of MAN, we had a meeting last summer and we said, guys, if we're going to have a partnership, what kind of low-hanging fruit can we actually solve together? And when your boss tells you you have to do that, you take it seriously. So I have to say, what we're getting ready to deploy with DNV is really something cool, and that is virtualization of the engine, right? We're feeding in data into DNV Veracity, looking at providing some classification and approval on each component real time. Now, there's no promise that that's going to come out to something in the next 9 months, but the speed at which DNV, yes, a class society, and MAN, yes, another OEM, the speed at which we're moving because of decarbonization is impressive. And that's why I'm saying, what can we learn from digitization and decarbonization together to speed things up? I think the other thing with partnerships is this fail fast mentality. We've partnered with a lot of folks who have unfortunately said they can do something in the industry to support us, and we've had to pull the plug on those partnerships. So for us, partnerships are let's fail fast, and that's the other piece of advice I would give for decarbonization. Do the experimentation, fail fast, and move on. Don't stick to one solution that doesn't work. If it doesn't work, drop it and move on. So I think this continued partnership for us, any of you in the room want to partner with MAN on the digital front, come see me, because we can fail fast or we can make something happen, right? What's next? So we're going to continue to support the decarbonization effort in MAN. You, as our customer or partner, will continue to see strides that we're making in providing analytics, the right kind of data to ensure that you're compliant, to ensure that we're continually coming out with new engine designs that meet the requirements of the industry. And again, as I said just now, no one can do it alone. That includes engine design, that includes decarbonization, new fuel types, hydrogen, all of these elements. Vessel efficiency is my favorite because everybody wants to jump on that one. You can't do it alone, so partnerships are the key. So again, I'm not selling anything from MAN. I don't even think I have an MAN logo on my presentation, but I did want to share the correlation between digitization and decarbonization. So our mantra is moving big things to zero. So we make the big things in all the industries we serve, so we have an obligation to move them to zero. So we ask you to partner with us, come join us, and help us move big things to zero. Thanks.
Thank you, Gregory. Very inspiring speech. Our next speaker today is Matthias Winkel, Managing Director of CM Technologies. Matthias will speak on digital tool to ensure energy efficiency. Sounds familiar somewhere.
Many thanks for the introduction and welcome to this hopefully exciting presentation I will show you today. I'm a marine engineer with, I think, reasonable understanding about technical things going on board ships, but I have no understanding whatsoever about computers and I have no understanding whatsoever about software. So, and here I am talking to you about digitalization on board ships. But I do have a mobile phone, and I have just been classified by Gregory to be a technical expert in digitalization. So I think I can tell you something interesting. I will look a little bit more from the technical side onto digitalization on board ships. And in the center of my presentation, I have my lovely friend, the chief engineer, which you can see on the slide right now. What is it if we talk about combustion optimization? We want to reduce fuel and everything. What is it what we look for? Is the first question always, what do we need to judge the engine efficiency? What is it? It's information about the conversion of the energy, and that happens during the combustion process. The combustion process is the only process where you can do something once your ship is at sea and is running. Everything else has been done by Gregory's colleague when they designed the engine, but after the engine has been built, the combustion process, and I include into that the turbocharger and all the processes around that, but that is the key point and the only point where you can do something to improve the efficiency. And the only way to find out something about the efficiency is you need to indicate the engine. That means you need to measure the pressure over one cycle. That will give you the information you need. What is it good for? Why we are doing that? And we are doing that from the very beginning. Indicating engines, it's improving the fuel efficiency. So we obviously want to save some money. We want to reduce the emissions, so we all talk about decarbonization these days. So here we can at least reduce the carbon amount to a certain extent. And we want to optimize our engine conditions. So we don't want to shake it all the time around as much as it can. We want to run it as calm as possible over the sea. So this is a typical diagram you get from when you indicate an engine. We have on the Y scale, we have the pressure, obviously, and on the X scale, we have the crankshaft angle. And that is more or less something out of the textbook. And what we can learn from it is, first of all, the compression pressure. That's easy and simple. We also have a maximum pressure. And we obviously have a point of ignition. That's the time when the fuel starts burning. It's not the time when the fuel gets into the liner, into the cylinder, but it's the time when the fuel starts burning. And we have obviously an end of combustion because everything needs to end. And so it is for the combustion, and that gives us the duration of combustion. And then you can add a few more sensors to your indicating process. And as just one example is having an acoustic emission sensor on the fuel pump, for instance, that can give you the time when the pump spill closes. So the fuel pump starts to do something, and then the next point it can give you is the point when the nozzle opens, so when actively the fuel starts to go into your liner, and that gives you the injection delay, and with the point of ignition also the ignition delay, and you can have the time when the nozzle closes, and that gives you the duration of injection. But all this looks quite simple here, that is drawn here, because this is more or less a textbook curve, and that's not how it looks into reality. There it's much more complex, I have to say. What we do is we expect from my friend, the chief engineer, to take the measurement and to make sense out of it. Not always, but in quite a lot of cases. And I personally think it's too much for this. for this guy. It's I don't say it's over his limit, but it shouldn't be his daily duty to do this. Just to give you one example for a measurement on a test bed, and this is a real example from where a German engine manufacturer, and it was not MAN, but another German engine manufacturer, has handed over an engine to a final customer, and what they do is they measure maximum pressure of the cylinders to show that the engine is very well balanced, and that gives the deviation of the maximum pressure what they have measured, and they all have been quite proud that the engine is quite well balanced. But if you look to the total curve, that was a quite modern engine, Tier 3 engine, which has a quite late combustion. There you can see the picture looks different. So what they actually measured was not the maximum pressure, they measured the compression pressure, but thought they measured the maximum pressure. Yes, it is the maximum pressure in this curve, but it's not the pressure they want to measure because it's not the pressure generated due to the combustion. That is completely different, and if I look at that one, I think it's easy to see that this engine is not totally out of balance, but for a brand new engine, I wouldn't have taken that engine. But the customer fortunately saw these information, and so he took the engine, everything was fine. What I want to show you with this one is we expect the chief engineer to do all this. I doubt this is going to work. What is the common way these days on board of ships, not on all ships, but on quite a lot of ships, is the chief engineer has to take the data. And there's no way around that he has to do something because there's a good reason for him to be on board our ships, and he has to take the data himself. Possibly not himself, so it might be his second engineer or third engineer or whoever is responsible for indicating the engine, but someone on board the ship needs to take the measurement. And then he loads the data into a PC, and he's a quite happy man. As we can see from the picture, he looks quite friendly. And then he sends a report to the office, and often as a PDF document or as a hard copy, and the superintendent is not looking quite happy anymore because he has quite a lot of things to do. And if the report, which is coming from board the ship, has doubtful results, he can't do anything with it. So because it's just a hard copy, it's not going to work at all. And he has quite a lot of other things to do. So it shouldn't be his daily job to evaluate these readings. So he's not the right person. What is the result out of that? The chief engineer gets frustrated and doesn't look into the data anymore. And the chief engineer is expected to deal with the problem on his own. As you can see, he's also not very happy, starts to get angry because he can't make a clue out of the findings. And the main engine is often relied on online systems, if they have online systems, or on whatever. And the auxiliaries very often are totally neglected. That's the situation we found on many ships these days. Performing the analysis, who can do that? Who's the right person to do that? I think we all agree the chief engineer he can do the measurement, but the later analysis, he's not the right person to do that. The chief engineer, the superintendent, he has quite a lot of things to do, and to do a good analysis. So a dedicated marine engineer from our office who's doing quite a lot of these analyses, it takes about half an hour, and taking in mind that you have 4 engines minimum on each ship is 2 hours work. And if you are not experienced in doing that every day, it's possibly even more time to do these analyses. So it doesn't fit in the normal scheme of a superintendent. He shouldn't be responsible for this. So what it's needed in our eyes, it's to have a dedicated marine engineer who can do this job. And he should be experienced with diesel performance analysis to do this job. He should have the time to do the analysis. And he can be an internal or an external guy. There are shipping companies who hire special guys only responsible for the performance of the main engines of their ships. And that's a good idea to do, but not every company can afford this guy. And there are external guys available who can provide the service for them. And now I'm talking about digitalization. So from our point of view, a good concept for engine performance evaluation is we have the chief engineer who takes the measurement. I said that earlier, there's no way around. He needs to do something. He needs to do the measurement. Then he sends the data into the cloud, into a cloud service. And then we have an external or internal marine engineer, and he can evaluate the data. He evaluates the data and he discovers the problem. And then he tells the chief engineer what the problem is and what the solution could be. And then the step goes on, so it's not the end of the story. Then the chief engineer is taking out his spanner and adjusting the engine accordingly. So he's doing something, again, according to the recommendation. And he then obviously takes another measurement and sends it back, and the complete process starts from the beginning regarding the evaluation. The chief engineer at any time, he can concentrate on his normal duties. And you see he's now looking much more happy with a fresh cup of coffee, and he's now looking much happier. But he has at any point access to all the data at any time, anywhere. So we know all very well that the superintendents, they are traveling around quite a lot, but they still have to answer questions from their vessel. So he should be able to access these data at any time. The fuel consumption is optimized and no engine will be neglected. That is very important. Most people are only looking for the main engine because that is the main thing consuming the fuel, but we shouldn't neglect the auxiliary engines, which have still a significant impact to our carbonization. And if you want to reduce it, that is the right point, or that is one point to start with. What is paramount? So we are talking about digitalization here, and at these conferences we have a lot of digitalization, and we have screens and monitors and a big screen here. And then we have a gentleman in the end, and I'm always trying to look at him, and he's lifting up cards telling me how many minutes I still have left over for this presentation, so that's why I have to look from time to time to him. What is paramount for a successful indication? It's a simple task. It needs to be a simple task with limited areas for mistakes. So it should be easy and simple for the chief engineer to do the job. Otherwise, it's not done. We need to have enough accuracy to do the analysis later on, so there's no point if I have cheap data going into a system, and I might have a complex system and very experienced marine engineer evaluating the data. If I have cheap data going in, cheap analysis is coming out. I need to have the possibility for a quick check for data reliability on the device. So the chief is not very happy about it if he has measured a complete V18 engine, 18 cylinders, going up to his computer and transferring all the data, and then he finds out, oh, one cylinder wasn't measured properly. So he needs to go back and start all over again. It's much better if he is at the engine and sees this cylinder wasn't measured correctly because for whatever reason he hasn't completely opened the indicator valve, or there are 1,000 other reasons. He can at once repeat that one measurement for that cylinder. That saves him a lot of time and makes him happy. Also very helpful if you can input your additional parameters straight at the engine. There are always parameters which are important, but which you need to read by hand as a fuel pump index or exhaust gas temperature. Those informations are important, but the device should allow on an easy way to put in these data straight into the device. And an easy data transfer. So it shouldn't be a big hassle to get the measurement onto other computer or whatever it is, or a cloud system. So that is paramount for the indication to make it a success. And now the requirements for a cloud system to have the loop closed again. So first of all, we need an easy data transfer. So the best is if the device you use for measurement can transfer the data straight into the cloud. And that's easy and simple. There shouldn't be, for a cloud system, there shouldn't be a limitation to one manufacturer of devices. And that's, I think, very important, because it's difficult to go to a customer and sell him a cloud system and tell him how wonderful this cloud is. But dear Mr. Customer, by the way, all the measurement devices you have on board your ships from the 3 different suppliers, you need to throw away and you need to buy ours. It's not going to happen. So the cloud needs to be capable to read data from various different systems. Results should be, and that is the beauty about digitalization and cloud systems, available anytime, anywhere, and by anyone. Obviously not by anyone, only by those who are allowed to access the data. But different people should have access to different data. That's very important these days, especially when we travel around. What is also important is that the devices we use to measure or to indicate the engine, they need some settings for the engine to get correct readings. And while we have a connection between the remote cloud system and the device, we can also use the other way around, and sending data back, engine configurations back to the device, so that the chief engineer doesn't need to hassle around with those. Very important in our eyes is easy and quick external help. There are always questions, there are always problems, there are always areas where people don't understand why is it and why is that. There need to be a phone number which I know I can call and where I get professional help. That's important. And obviously, but that's coming with all these digital systems, that you can have a history of your vessel or compare other vessels, sister vessels, and same engines on the same vessel, and so on and so forth. So that's important for a cloud system if you want to have it a success. What can we now gain by digitized analysis? It's optimized fuel consumption. Obviously, it's a good combustion, optimized combustion, getting most out of the energy we are putting into our engine, and optimized maintenance system. So we don't want to maintain our engines as much as possible. We want to maintain our engine as much as needed. And if we want to optimize it, we need to measure the condition of the engine. No way around. And a few ecological effects of ignorance, if I just run the engine as it runs, because it still runs without all these wonderful things, but take in mind that each degree delayed combustion, and there's always a movement of the ignition point on board ships, I can tell you, but each degree delayed combustion increases exhaust gas temperature by about 8 to 10 degrees. And that increases the fuel oil consumption by approximately 2%. So if you think about what we do to reduce our fuel consumption by 2%, that's quite a lot. So here is a good area to improve the fuel consumption. And just looking from a different angle onto these data, if we are capable to increase the Pmax, and that is all what it is about, so we want to bring the Pmax up as much as possible to get most out of our engine, it's each bar we are able to increase the average Pmax. It's about 0.25% reduction in fuel consumption. Thank you. 1 minute left. What is the conclusion out of this all? So anyone knows this guy? He's not very important. I don't him either, so I can't tell you who it is, but that's not important. His T-shirt is the important thing. And that says, in God we trust, everything else we test. So that means just believing that our engine is running fine is better we use Sundays to go to church. But if we don't only want to believe our engine is running fine, we need to test it. So what are the ecological and economic gains through the digitalization process I just introduced? I think I explained that just a good diesel indicator is not enough. So it's not enough just to buy a device and supply on board the ship. And here, Mr. Chief Engineer, it's your task to do something with it. A specialist is needed for data analysis, so we shouldn't leave the chief engineer or the superintendent alone with his job. And a practical digitalization is needed. So we need a sort of cloud system or something like that to communicate with the ship and to bring everything together. And that is helping to improve the efficiency of our vessels. That brings me to the end of my presentation, very well in time. Thank you very much.
Thank you very much, Matthias, for a comprehensive run through of what I actually did when I was younger. I remember all that quite a bit, so that was interesting. Thank you. Our last speaker in this session is Pascal Riolong, Head of Digital Product Management at the Digital Division of Acceleron, formerly known as ABB Turbo, we just learned, talking about the significance of data in achieving sustainable performance. Please.
Thank you for the introduction. I wanted to ask, how is a digital solution for vessel efficiency monitoring, how is that now related to future fuels? But in the preceding presentations, we have learned it. It's, of course, because we are in a transition period, away from fossil fuels to carbon neutral. And it's now also the time where the regulations and the financing standards, they force the shipping industry to act when it comes to a decision about investment in new modern technologies, but also when it comes to the efficiency of the existing fleet. Vessel fuel efficiency in the past decades, it has mainly been the concern for those who paid for the fuel bill, for the charterers, and in periods with high fuel prices and low freight rates. Their influencing activities around COPEX focused on their core business, the voyage planning, weather routing, and the logistics. Equipment optimization between the dry dockings, only on schedule for organizations having strong technical departments. I realize now, standing here in Hamburg and saying it, Hamburg, where so many reputable shipping organizations are located, is a bit risky, but if you allow me the provocative statement, globally, I have heard often, why worry, plant maintenance is done, engine is running, ship is sailing. That, of course, inevitably leads to disputes around performance. Looking at engines. Engine fuel efficiency, two inputs are needed, flow meter and torque meter. Both expensive, sensitive devices need to be properly installed and calibrated. They deliver the flow and the shaft power. But then on top of it, we need inputs for ISO correction and eventually also need to deduct strain amounts from the fuel pumps in order to finally compare it with the shop test result in the specific fuel oil consumption diagram. So don't worry about more diagrams this afternoon from my side. It's just for illustration that we have here quite a high variance in measurements which a crew took on board of a tanker vessel during 2 years in the monthly performance run. Compliance with charter party is often proved by speed consumption tables, speed consumption curves. Next to the absolute observed fuel consumption, the vital input is speed through water from the speed log. In order to normalize it and compare it with sea-trial and or charter party baselines, we need additional inputs for sea and weather conditions, also influence of draft and trim. It is needed when we want to compare with normalized values according to ITTC, for instance. So also that example shows high variance compared to sea trial, but then also in the charter party baseline, which fits much better to the cloud of points, still we have a high variance. These examples I have put together to illustrate that compliance with charter party agreement is hard to prove, but because all the vital inputs are difficult to measure in the first place. So that means safety margins are always applied to these baselines in the charter parties. In the past, but still today. Now, times are changing. We have new standard for hull and propeller performance measurement, the ISO 19030. There are better sensors, better measurement equipment. The digitalization in general supports us greatly for data acquisition, transmission, data storage, data evaluation. There is now a variety of solutions in the market available to support those who are ready to invest in it and to gain insights into fuel efficiency now in a time where the fuel prices rise. However, what brings it on everybody's table, finally, is the carbon intensity indicator. Now the different parties ask themselves questions, starting with ship owners and ship managers. On the long term, they ask, how are our ships operated now related to CII? What will the year-end result of our ships be? And could we still change operation to finally still attain the required CII? On mid-term, it's the risk that as the EMP Part 3 has to be amended, an investment into energy-saving devices is needed. What is the influence of customers on the charterer selection? And will Poseidon principles, quite likely, drive the financing and insurance sector to give better conditions to the most efficient vessels only? But also the charterers have concerns. What about the owners' thoughts about CII? How will that impact our chartered vessels' operations? What will be the basis for discussion around operational measures to improve the CII? And last but not least, are the vessels we have currently chartered meeting the sustainability requests of our end customers? This is why we have identified that there will be a much closer cooperation on operational matters. And I was quite surprised last week that also BIMCO has amended the time charter part with a CII clause. So I think we are definitely on the right track here by proposing an interactive display of a ship's CII accumulation year to date, including a forecasting of the end of period CII. It's part of Accelleron's mission that we look at things which make our customers' business better, and we look at this business in its entirety. We're having a long-term track record in the field of turbocharger design, manufacturing, and servicing, and by that also an inherent expertise on marine diesel engine performance. In the past 5 years, we have developed a number of digital architectural building blocks for remote diagnostics solutions around the turbochargers, around the engines, and this we are now also leveraging to the system vessel, to the level, because this is what our customers' business is about. We took a strategic decision some time ago that we are not installing any hardware like sensors or edge devices on board of the vessels. We want to generate value out of existing infrastructure, and by that also increase the return on investment on the same. That's why we are connecting to electronic logbook systems and Noon report systems through third parties who upload that data to the cloud, and from there we do a cloud-to-cloud data transfer via Azure Event Hubs or REST API. The data is then stored in the Accelleron high-efficiency time series data storage and enriched with data about position, sea, weather information from external partner. The business logics layer also fully sits in our cloud. We have on the one side the voyage detection algorithm, which you're going to see afterwards, and the CII calculation year to date, including also the CII forecasting framework. The last two have then via API the connection to our customer portal, where this analytics sits in a dedicated module and can be used by the users in the shipping company's office. Also, when it comes to data requirements, we have nothing reinvented. We base it all on the IMO DCS standard, just adding the Noon reporting. So we need date and time for all the events. We need remaining on board per fuel type for port entry, port exit, and noon. We need the bunker amount for the bunkerings, and we need the distance traveled for port entry and noon events. The draft we only require for our forecasting feature, which we're going to see later on. But first, all these incoming events need to be brought into a structure like we see in the right, where voyage and port stay follow each other in a sequence. This is what we call voyage detection. So if we have a look at the top here, vessel is sailing, doing port exit, noon, maybe bunkering, port entry, and so on. And our algorithm goes through that series and detects first event and last event. So first event is the port exit, last event is port entry. What is between is a voyage. And the distance, the fuel consumption per fuel type is calculated by remaining on board of the last event minus remaining on board fuel first event plus the sum of all the bunker amounts in between. Same applies for the port stay. There the first and the last is just flipped around. For the distance traveled, for the one system we have worked with, we had to sum up all the distances of the noon reports because the crew was instructed to report each noon distance since last noon report. So this maybe is not rocket science, but still somebody had to put her mind around it to get that done. But then we take that to the next level, because now we are putting all this voyage and port stay data in the graphical CII chart. We see here this y-axis is the CII rating bars, and on the x-axis we have the time. Now each black line is a voyage, and each purple line down there is a port stay obviously not having a CII. Each voyage CII is calculated in the same way like the full year's CII is calculated, and there is now initially in that example a voyage, some voyages with a very high CII. Question is that of a concern? I can tell you actually it is not, because ship may have been drifting, using auxiliary power, not sailing too much of distance, other reasons like we also have heard, waiting time, for instance, in front of the port. But to really illustrate it, we, as a next step, add the accumulated CII to the picture. The accumulated CII, the blue line, is calculated after each voyage and after each port stay with the same formula like for the full year. And now we see that this first voyage with a high CII in the beginning of the year had quite an effect. We started in the very beginning just at the level where the first voyage was. Then the average, the accumulated was pulled up quite a lot, but then it smoothens out the more lower CII voyages occur. Of course, we're getting out also in this initial view the year-to-date CII, which is in the very right in that case. And now we could say maybe that's a fair assumption where we will also end at the end of the year if there is unchanged operation and technical factors. Unfortunately, this is not the case. These factors are going to change. And this is why we add on top of that display about the historic CII information, we are adding the forecasting feature. To understand forecasting, quickly go through the drivers of CII. I'm not repeating here any CII webinar, which you have maybe attended in the last years, but just to be on the same page. So from my understanding, ship speed, of course, highest contribution to CII because it has a cubic relation to the propulsion power required. The cargo has an influence because cargo impacts the draft of the vessel, and via the draft there is more propulsion power required per sail distance. So even though cargo is not in the CII formula as such, it is relevant for the forecasting. The port stay duration as well. Port stay, as said, no distance traveled produced, still emissions. On the technical side, it's clear hull and propeller performance is the driver, with hull aging, fouling, cavitation giving substantial amounts to the CII. Fuel type and engine performance also go together now. Here I'm also excluding fuel type conversions, but just changing from HFO to diesel, for instance, they have a smaller contribution. So that all in all is only a qualitative view, and the birth just indicates the approximate relevance. Good. Now we want to allow the user to make a simulation. So in the simulation panel, we list all these indicating influencing factors. Enlarging a bit here. And then based on the historic date range, which can also be changed, here is 1 year, we propose for each parameter what was the historic value we have identified. Going back to the CII chart, it's now extended to last year plus this year, because I want to show you here the year-to-date CII and the historic date range. It immediately calculates forecasting for the end of the year with the historic parameters, which have been retrieved, plus a standard hull aging rate of 1%. So even though we are now at this point, because the historic values were much lower, it's forecasting that we are ending in a reasonable range, somewhere a lower C rating range. But now, in the next step, user can simulate different scenarios. For instance, increasing the ship speed, because there is a new charter party upcoming where a higher contracted speed is included. Or change the average hull aging rate per month, because the ship is expected to be operated in tropical conditions. Clicking on Recalculate, again going back to the CII forecasting chart, now we see the different scenarios, like could we even afford ship speed, or would it maybe be better to play it safe and reduce the ship speed and additionally also clean the hull. So I'm keeping it short as the last presenter, and I'd like to summarize here. We're proposing an automated system for CII tracking, because this enables the early decision making, and it's all based on data. We run different simulations for various scenarios, and by that we are increasing the transparency, we're boosting the awareness and the cooperation on the way to decarbonization. Thank you.
Thank you, Pascal. I think we could have a very long discussion about the beauties of CII, but I don't think we should have that at this conference. There are other conferences and where this is probably more appropriate, but we should all remember that the most efficient ship out there in a CII context is empty, sailing equal speed, and never calling a port. That's and maybe I'll leave it with that. You know, just because there are perspectives to this which are important, of course. What I think we should do now, because we are somewhat pressed on time, I would like you to reflect a little bit on something that was not so prominent in any of your presentations. That's actually the concept of having standards for what we're discussing here. And I think you were alluding to it, each of you, in various ways. For example, in terms of not having proprietary products and open standards or open systems, but really the role of standards in terms of data communication, if we really want to accomplish the big picture thing with data. And I will start with you, Mia, if you could reflect just short on this. Thank you.
Okay, now it's on. Well, I mean, of course, like for this digital modeling as well, so typically we need some data anyway. So basically, of course, the standardization of the collection method, and so that gives more confidence to quality, and so that it's on the kind of same level. I'm not really sure if I answered kind of correctly your question, but it's just these projects. Because I would say even if it's a new building, but especially with if dealing with retrofit making model, so it's such a kind of complicated task. First of all, to get the data, where it comes from, understand, clean it, even there's a kind of standard process anyway in order to use it as input for the models. So the more this is standardized and help kind of in that, so it will make our work also easier. But I think my neighbor is better to comment on the data.
Thank you, Mia. Gregory, what is it?
Yeah, I think, well, as an OEM, data ontology standardization is very critical. I mean, we at MAN, we can actually onboard a four-stroke engine, for example, into our ecosystem in about 25 minutes. Now you say, what does that mean? That means that if we retrofit a four-stroke engine, or let's say 5 engines, because we have a digital twin already built in PLM through the whole topic, we're able to quickly onboard that. So for us, all of our reliance and checking and data quality checks are all built into that. We have a baseline. But I think the more interesting question is the industry standards of data quality. You know, do we do ISO as proposed by some of the class societies, or how do we come to an overall standard? Because in the previous industry I was in, which was the aggregate mining and construction, we had the ISO standard for fleet owners, so that a fleet manager could look at 25 to 50 different indicators and get the same picture, irrespective if he had a Caterpillar engine or a Volvo. So I think the standardization of data from the birth of an asset is extremely important, and then the continuous check against test bed and other criteria to maintain that baseline is one piece. But the bigger question is, how do you all feel about this standardization of the ISO, which is proposed by class society? That's my question, I guess. But somebody else should ask that, I guess.
Maybe we can have class to answer that question. Matthias?
Yeah. I think standardization is needed and is important, but what we have in the way of standardization is always a competition. So problem is one company doesn't want to read the information from the other company. And that's not always correct and right, although many companies are doing that. And I have learned once from a clever guy that it is for a company very powerful if you have a lot of information in your company. But it's even more powerful if you give these information away to your clients and to your customer and to the world, because that's helping you growing much more than the other way around. But that's difficult to bring that thinking into everybody's brain and mind. And that is the problem with standardization of data. And in the end, it needs someone from the outside to force these processes, regardless whether it's classification society or whomever. I remember how complicated it is to make all mobile phone manufacturers. We just talked about mobile phones. I'm coming back to the same subject, to have the same power charger connector, something very simple. And it took the EU a couple of years to standardize that. And we are still not there. And that's the same problem, I think, with data standardization. It just needs time, but I think people will understand that it's important that we all work onto the same level, and that's not good that everyone does his own thing. Otherwise, digitalization is not going to work.
Thank you. And Pascal?
I wanted to say similar thing like Matthias said. I believe that the data produced on these assets belongs to the owners of the assets. And we, as OEM, we should be also open to share it and don't leave the burden on the shoulders of the customers to bring us together to share it. And this, in my experience, has been an obstacle in quite many digitalization and optimization projects in the past.
Thank you very much. And I think when we discuss standardization, it always reminds me of the car industry, and I continue to be amazed that I can actually use the same device to plug into my US-made Ford and my wife's French-built Citroën. And it kind of works on the same protocol. It's the same device to measure. It's the same PID numbers, everything. It seems to be kind of the ultimate standardization in terms of measuring on something which is common on all ships, which are the engines, for example. And is that something that could be learned in this industry, or is this taking it too far?
I don't know, my point, and I'll just give an example. When I first connected 5 brand new vessels, and they were all sister ships, right? And I was out in the field connecting them. They were all different. The engine data was the same, but the alarm management system was completely different from sister vessels. So I think it's beyond the engine. I think, yeah, okay, the engine, our models are pretty standard, but I think it's, as you mentioned, who should derive it at the design of the vessel, right? Is it the standardization that starts with a design? Because if you look at the automotive industry, the automotive industry has 2 different consortiums. They have the OEMs who all agree, and then they have, let's say, the users or fleet management folks that started the standardization. So it starts with the OEMs, but I also think it starts with the builders as well, right? I mean, will the regulatory agencies be able to standardize that? I guess if there's standards around certain reporting in the future, it'll certainly have to come to some conclusion there.
We know at least that IMO is working on a standard data reference model, which is pretty open for input, and I think I think we could conclude here that, or I could plead to you guys to actually take part in this work to expand that data model, because the larger it gets, the more data reference points are in that model, the more likely it is that people will use this in their various systems. That's one thing. I think with this, we have a number of questions on the screen. You have all seen them, but I don't think, unfortunately, we have time to go through this. We're a little bit pressed on time, and the coffee is getting cold. So I would like to thank the panel for some very interesting presentations. And before we let them go, I have to hand out a little thing, but let's give them a big hand while I hand out a little token of appreciation. Thank you. And while I do that, please be back in the room for the scheduled time after coffee, which is 3:30, I believe, isn't it? Thank you.